All right, Calculus 12, here we go. We're doing Trig again, part 3. Big stuff happening here in the Trig world. So today, Trig derivatives again. We're on 7273. This is part 3. I know it's a long time to go through this, but this just shows you how long it takes me to convey this information to you. Is you need to steep in this really deep and do this well. So we're going to practice today the trig derivatives, but then with the critical numbers, points of concavity, points of inflection, all that comes into play. Just a cap of what you should be starting to practice already, and this is just to make sure that you're not getting overwhelmed, because there's a lot of stuff and you just have to practice it. It's like exercise. You just cannot get in shape with this without doing it. So for 7.2 and 7.3, the first 3 questions on both sections are really good just to get the rules down, just your basic rules and all of those 6 derivatives that you should know of your sine, cos, tan, cotan, secant, and cosecant. And then on those same sections, 4 to 13 on both, which is nice that they're both the same, those are just a mix of doing other stuff, finding tangent lines, critical numbers, curve sketching, points of inflection like we're going to look at today. And you will find the hardest part, once you get past just knowing the rules of derivatives for calculus, it'll be your pre-calc 12 that'll come back to hurt you. It'll be like identities, it'll be solving trig equations that'll bug you the most. Or in some ways they shouldn't bug you, it should be comforting, but it will be the part that'll be, oh man, I gotta remember that. Yep, you do. So here's our first example. Find the critical numbers for this function. So 2 things here. One is, remember what critical numbers are before I even look at this function. Critical numbers scream first derivative where it equals 0, first derivative where it does not exist, and any endpoints. So that's the first thing you want to glean from this. The second thing is I need to now take the derivative, and then that's where the new trig comes in, because now I'm going to take the derivative of this. Now before I take the derivative of it, let's do this. I'm going to rewrite, first of all, that cube. I don't like the cube written like that. I'm going to write it like this. And same thing with the square here. I'm going to write the square like that, just because I can see the layers better. So the derivative of this individual term, because there's sum of difference, I can do the individual bits. The 3 is the outer function. The 3 comes down, multiplies the 2/3 to give me 2. Inside stays the same. Technically it lowers to a power of 2, and then I got to multiply by the derivative of the inside, and the derivative of sine is cosine. Plus the next one. Okay, it's similar. So the half comes down, multiplies the 5 halves to give you 5. Inside stays the same, lowers to a power of 1 technically. Got to multiply by the derivative of the inside, and the derivative of sine is cos. And the last one is just a really basic one. That's just a coefficient out front, so that gives me 3 times the derivative of sine. No tricks here, is cosine. Let's make it look better. So this gives me 2 sine squared cos plus 5 sine x cos x minus 3 cos x. So that's practice of old skills. This is also old skills. Now the 2 meet. I now need to figure out where this equals 0. Alright, so let's do this first. Where does this equal 0? And now how do I solve that? And all of a sudden it becomes a trig equation from pre-calc 12. So when I see this, my first thought would be, thank goodness there's a cos in common to all of them, so I'm going to factor out a cos. Factoring is usually something that makes me feel safe and on the right track. If there wasn't a cos there, I'd be I might have to go to Desmos and use technology to get it. Then also what I'm left with is this looks like a trinomial that I could factor from pre-calc 12. Some people might have let this be u, so you get 2u squared plus 5u minus 3. But this factors into 2 sine x and a sine x and a 3 here. This becomes a 3 plus, and that's a minus 1. I would just double check. 2 sine squared, 6 sine minus 1 sine is 5 sine. There's my minus 3. So it's all factored, and then out of this, out comes the fact that cos theta or cos x can equal 0, sine x can equal a half, and sine x can equal -3. So a few things that should come back to play. Remember sine, remember, only looks like this. It can only go between -1 and 1. -3 is outside its limit, so to speak. So this gives me no solutions. That's nice. So that branch, nothing. This screams to me cast rule, because remember, it didn't give me any limitations on the angle. So this could be general solutions. I look at that and say, oh, this is positive. Remember your cast rule. All suckers take cocaine. So where is it positive? Here and here. What's your reference angle? The reference angle for 1/2 for sine is pi over 6. So the first answer out would be pi over 6. And the other answer out would be, remember this is your reference angle, and here would be pi 180 minus pi over 6, or 5 pi over 6. But because we're dealing with multiple answers, you can add to both of these 2 pi n. 2 pi n, the period of sine. Remember, n is an element of the integers. So that there's a whack of critical numbers here. Every pi over 6 plus 2 pi n, and every 5 pi over 6 plus 2 pi n. And then also for cosine equaling 0, for me, I like to use the cos graph to help me. There's my little cos graph in the first between 0 and 2 pi. Where is it 0? It's 0 here at pi over 2, and it's 0 there at 3 pi over 2. So there's 2 more answers out of here. Pi over 2 plus or minus, or plus, you can do plus or minus, but I just do plus 2 pi n, and 3 pi over 2 plus 2 pi n. So we'll come back to that in a minute. Got a lot of critical numbers there. Are there any does not exist derivative issues? So is there any square rooting negatives, dividing by zeros? Thank goodness there's no denominators here. So this has none. And endpoints would be either given directly, and there were none, or it'd be built into the domain. But because sine can take any angle, there is the domain of this is all real numbers, so therefore there are no endpoints. So thank goodness that was big enough as it was. My critical numbers are, let's list them all out, pi over 6 plus 2 pi n, pi over 2 plus 2 pi n, 5 pi over 6 plus 2 pi n, and 3 pi over 2 plus 2 pi n. Whew! Alright. And the irony of it is, the only, well, there's a bunch of calculus in here. The critical numbers is the calculus concept. The derivative is obviously the calculus concept, but then the solving, pre-calc 12. Okay, next guy. Find the points of inflection for this function, sine of x plus cos of x. 2 things. Points of inflection scream second derivative equaling 0, or it could be also does not exist, and concavity change. So it must change concavity. So there's the big picture. I obviously then need to use my derivative skills. The derivative of this, thank goodness, is not too bad. Derivative of sine, cos, derivative of cos, negative sine. Second derivative is the derivative of the first. So derivative of cos, negative sine. Derivative of negative sine would be negative cos. Now just double check we haven't made any mistakes, because I don't want to miss a minus sign. Derivative of sine, positive cos. Derivative of cos, negative sine. Derivative of cos, negative sine. Derivative of negative sine is negative cos. Okay, we're good. So, first of all, let's find out where it equals 0. So where does this equal 0, which could lead to possible points of inflection? How do I solve that? No factoring, there's no identities, but there is one thing here. If I move this sine over to this side, and then get sneaky here and divide by cos, I end up with -1 on this side, and here I end up with tan. And then I can solve this equation. I can say, oh, cast rule. Where is tan negative? Here and here. And what's my reference angle? For 1, for tan, is pi over 4. So this is pi over 4 and that's pi over 4. So my first answer is pi minus pi over 4, or 3 pi over 4. And my second answer all the way around to there is 2 pi minus pi over 4, or 7 pi over 4. And I am limited by the restrictions here, so thank goodness I'm only going to 0 to 2 pi, because I don't have to worry about adding on the period of tan, which would be pi. Are there any does not exist? Thank goodness again. Now you could argue I have created an issue of denominator, but initially, if I look back at the original second derivative, there is no denominator, so this is none. So what I need to do next is I need to go to a second derivative number line, because this isn't enough. These might be points of inflection. They may not be. So here is, and put it just for a reference, I'm going to put, I like to put these on there because those are my nice little 90s, 180s, 270s, 360, and my 3 pi over 4 is somewhere in here, and my 7 pi over 4 is somewhere in here. So now we need to show that concavity does truly change, and then I got to check, which takes a little bit of work. So I'm going to go and check, I'll check pi over 2. So let's go to my second derivative and plug in pi over 2. So plug in numbers that are easily evaluated. So here it is. What is sine of 90? Sine of 90 is 1. So this will be negative 1. And what's cos of 90? Cos of 90 is 0. So this is going to give me negative 1. So I know this is negative here. So that means it's concave down. Now let's try the second derivative at pi. What's sine of pi? I have to think about the sine graph. Sine of pi is 0. Cos of pi is negative 1. But it's a negative in front, so that spits out positive 1. So now I can see this is positive concavity here. It's concave up. This is a point of inflection because concavity changes. And then for the last stretch here, I'll maybe plug in pi over 2. So f prime of pi over 2, which is like 0 in a sense. So sine of 0 is 0. And cos of pi over 2 is 1. That's negative 1 again. So it's concave down. So points of inflection are 3 pi over 4 comma f of 3 pi over 4. I could go and evaluate that and get a actual value with my skills, but at the moment I'm just going to leave it at that. And there's my 2 points of inflection. So good review of points of inflection. Second derivative equals 0 or does not exist, and concavity must be proven to change, along with my derivative skills. Alright, I would recommend in the textbook, because there's lots of examples, like I could just do example after example after example. I could have YouTube almost filled up with stuff. It's insane. So go and check out these sections, look at the examples in the textbook, do practice on these first, get very confident just with the derivative skills. Just build up, if anything out of this course, get that out of it. And then comes the other skills that you've learned before, where that's just dealing with the old stuff that you've done. Again, really good review. There's a common thread running throughout this entire course, and it's really nice. But the trouble is that thread does continue throughout the course. I would say that's the best thing about this course. The things get reiterated over and over and over again. That's the worst thing about this course. Things get iterated over and over and over again. Okay, we're going to stop there. And that is trig up to the third unit, or third chapter, or third section in chapter 7. Over and out.